Welcome to Chapter 1, Session 3 of Jumpstart Honors Precalculus. Today, we will explore the exciting world of combining functions, understanding inverses, and applying linear models to real-world data. Get ready to build new functions from old ones, undo functions with inverses, and see how these concepts come together in modeling. Here's what you'll learn today. In Section 1.5, we will cover combining functions through sum, difference, product, and quotient, as well as composition. Section 1.6 will introduce inverse functions, including how to identify one-to-one functions and find inverses algebraically. Finally, in Section 1.7, we will discuss modeling with direct and inverse variation and how to create real-world linear models. Let's dive into combinations of functions. We already know how individual functions work, and now we will learn how to combine them to create new functions. In this section, we will define arithmetic combinations of functions. Given two functions, the sum is found by adding their outputs, the difference by subtracting, the product by multiplying, and the quotient by dividing, as long as the denominator is not 0. Remember, when combining functions, the domain of the resulting function is the intersection of the domains of the original functions minus any values that make the denominator 0. Now let's look at the composition of functions. The composition of function f with function g is written as f of g of x. This means we first apply g to x and then apply f to the result. It's important to note that the order matters. In general, f of g is not the same as g of f. For the composition to be valid, x must be in the domain of g, and the output of g must be in the domain of f. Imagine composition as a pipeline. The input flows through the g function first, and then the output from g feeds into the f function. For example, if g of x equals x plus 3, and f of x equals x squared, then starting with an input of 2, g gives us 5, and then f gives us 25. Thus, the composition of f and g at 2 results in 25. Let's work through an example of combining functions. Let f of x equal x squared minus 1 and g of x equal x plus 3. First, we find the sum, f plus g of x equals x squared minus 1 plus x plus 3, which simplifies to x squared plus x plus 2. Next, the product, f times g of x equals x squared minus 1 times x plus 3, which expands to x cubed plus 3x squared minus x minus 3. For composition, f of g of x equals of x plus 3, resulting in x plus 3 squared minus 1, simplifying to x squared plus 6x plus 8. Lastly, g of f of x equals g of x squared minus 1, which simplifies to x squared plus 2. Now, let's find the domain of a composition. Suppose f of x equals the square root of x, and g of x equals 4 minus x squared. To find the domain of the composition f of g, we start with f of g of x, which is the square root of 4 minus x squared. We need to ensure that 4 minus x squared is greater than or equal to 0, leading us to the inequality x squared must be less than or equal to 4. This gives us the domain of x between -2 and 2 inclusive. Always remember to check the domain of the inner function as well. Try these practice problems. First, let f of x equal 1 over x and g of x equal x squared minus 9. Find the quotient of f over g and state its domain. Next, find the composition g of f and state its domain as well. Remember to identify any values that make the denominator 0. Now let's transition to inverse functions. If a function takes an input to an output, can we reverse the process and go from output back to input? An inverse function is defined as a function g that undoes the effect of function f. This means that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. We denote the inverse of f as f inverse. It's important to note that f inverse of x does not mean 1 over f of x. The superscript -1 indicates the inverse function. A function is considered one-to-one if no two different inputs produce the same output. This can be expressed as if f of a equals f of b, then a must equal b. To determine if a function has an inverse, we can use the horizontal line test. If every horizontal line intersects the graph at most once, the function is one-to-one. For example, the function f of x equals x cubed is one-to-one, while f of x equals x squared is not. However, we can restrict the domain of the latter to make it one-to-one. Now let's see the horizontal line test in action. As we sweep a horizontal line across the graph of f of x equals x cubed, we notice that every horizontal line hits the graph only once, confirming it's 1-to-1. In contrast, for f of x equals x squared, a horizontal line at y equals 2 intersects the graph at 2 points, indicating it's not invertible. However, if we restrict the domain of x squared to x greater than or equal to 0, it passes the test. To find an inverse algebraically, follow these steps. First, verify that the function is 1-to-1. Next, write y equals f of x. Then swap x and y and solve for y. The result will give you y equals f inverse of x. Finally, check that f of f inverse of x equals x and f inverse of f of x equals x. Let's find an inverse with an example. Consider the function f of x equals 2x minus 5. Since this is a linear function with a non-zero slope, it is 1-to-1. We start with y equals 2x minus 5, swap x and y to get x equals 2y minus 5, and then solve for y. This leads us to y equals x plus 5 over 2. Thus, the inverse function is f inverse of x equals x plus 5 over 2. Finally, we can check our work by confirming that f of f inverse of x equals x. The graph of the inverse function is a reflection of the original function across the line y equals x. This means that if the point AB is on the graph of f, then the point BA will be on the graph of f inverse. Additionally, the domain of f corresponds to the range of f inverse, and the range of f corresponds to the domain of f inverse. As we visualize inverse reflection, notice how every point on the graph of f has a corresponding mirror image on the graph of f inverse across the dashed line y equals x. This geometric relationship is essential to understanding inverses. Now let's find an inverse for a nonlinear function. Consider f of x equals the square root of x minus 2, with x greater than or equal to 2. Since this function is increasing on the interval from 2 to infinity, it is 1-to-1. We start with y equals the square root of x minus 2, swap to get x equals the square root of y minus 2, and then square both sides to eliminate the square root. This gives us x squared equals y minus 2, leading to y equals x squared plus 2. Thus, the inverse function is f inverse of x equals x squared plus 2, with the restriction that x is greater than or equal to 0. Remember, the range of f gives us the domain of f inverse. Try this practice problem on inverse functions. First, show that the function f of x equals x cubed plus 1 is 1-to-1, then find the inverse function f inverse of x. Finally, verify your answer by checking that f of f inverse of x equals x. Let's transition to mathematical modeling. Now we will apply our function toolkit to build algebraic models that represent real-world situations. In Section 1.7, we will discuss direct and inverse variation. Direct variation occurs when y varies directly as x, which can be expressed as y equals kx, where k is the constant of variation. An example of this is the relationship between distance, rate, and time. Inverse variation occurs when y varies inversely as x, expressed as y equals k over x. In this case, as x increases, y decreases, and vice versa. An example is the relationship between speed, distance, and time. To differentiate between direct and inverse variation, remember that in direct variation, doubling x results in doubling y. In contrast, in inverse variation, doubling x results in halving y. This relationship can be visualized in their respective graphs: a straight line through the origin for direct variation and a hyperbola for inverse variation. Let's work through a real-world linear model example. A plumber charges a $45 service fee plus $70 for each hour worked. We can write a linear model for the total cost C as a function of hours h, which gives us C of h equals 70h plus 45. If we want to find the cost for a 3-hour job, we can substitute h with 3, resulting in C of 3 equals 70 times 3 plus 45, which equals $255. If the total bill is $325, we can set up the equation 325 equals 70h plus 45, solve for h, and find that the job took 4 hours. Try these practice problems on variation and modeling. First, if y varies directly as x and y equals 12 when x equals 4, find y when x equals 10. Next, consider the pressure P of a gas that varies inversely as its volume V. If P equals 150 kPa when V equals 2 liters, Find P when V equals 5 liters. In summary, we covered several key topics today. In Section 1.5, we learned about combining functions through sum, difference, product, quotient, and composition, along with the importance of domain. In Section 1.6, we explored inverse functions, including the horizontal line test and how to find inverses. Finally, in Section 1.7, we discussed direct and inverse variation and how to create linear models. This concludes Chapter 1, and in our next session, we will begin Chapter 2, focusing on polynomial and rational functions. Be sure to review the problems assigned.